Okay, here's a short video to cover basic gate functions for logic problems. We didn't actually have time to cover this in a lecture, but it is so easy. You'll pick it up really quickly. Okay, so basic gates have a number of inputs, usually at least 2 for an AND gate. So this is the shape of an AND. Okay, so this kind of shape is AND. All right, another shape is where you have a curved front end and it comes to make a point. This basic shape is OR. All right, then there's another one with this shape. It's got, not just an OR, but another arc here. This is called an exclusive OR. And then there's the NOT gate or inverter. It's also sometimes called an inverter. Okay, and then you can put, let me separate this a little bit. And all right. Sorry. Okay, there's also gates that have the same basic shapes, but you invert the output. So this would be a NAND gate, meaning not AND. Okay, and then this would be, a NOR gate, meaning not OR. And you can even do that on an exclusive OR. And when you do that, it's called an equivalence gate. Okay, so I would want you to be able to fill out what we call a truth table for all the gates. All right, so the truth tables are pretty easy. We only have 2 inputs on all these gates. You can have more than 2 for everything but the inverter. An inverter always has just 1. Okay, so let me do an AND gate with just 2 inputs. That would be, let's say A and B are the inputs. And what we're wondering is, what is the output? All right, these are all done with voltages, but we abstract this idea where 0 is a low voltage and 1 is a high voltage. So for high voltage, we mean something like 5 volts or 3.5 volts. It depends on the technology that we use. Okay, and so logically, you want to figure out what the output of A and B would be. So 0 ANDed with anything is 0. So this is the logic truth table for an AND gate. It's only a 1 if both A and B are 1, then the output is a 1. Okay, so that's pretty easy. And you could extend this to 3 inputs. Okay, all combinations of 3 inputs would be this, and so you'd be looking at A, B, C, and an output D. Okay, and it's the same thing. All of these have to be true for the output to be true. So the only place where you'd have a 1 is on the bottom row. Everything else would be a 0. Okay, so all this section is talking about Okay, We should also talk about the inverter at this point. Not, that's pretty easy. All right, so you only have an A and an output B. All right, so if you put in a 0, the inverter just changes the answer to a 1. It flips it over to the opposite voltage state. So if you put in a 1, you get a 0. All right, so not is very easy. Now let's go with OR. What if I had two inputs, A and B, and an output C, and I wanted to know what the OR function would be? Okay, then if either A or B is a 1, the output is 1. So the only place where it's not a 1 is when A and B are both 0. Okay? All right, so that's pretty straightforward. I'm not going to give all the combinations of these, but I did want to talk about a NOR gate, and you could do the same thing for a NAND gate. So if you had a NOR gate, that's taking the same function, only this bubble means invert. It means as if you'd put it through an inverter or a NOT gate. Okay, so if I had A, B, and C, I could write down the output here by writing down the combinations of A and B. And rather than a regular OR like in this column, you just flip all those over. All right, so this would be a 1, 0, 0, 0. So this would be the truth table for a NOR gate. You can do the same thing for a NAND gate. You come up here and you would flip the output, and so for a NAND gate, the output would be 1, 1, 1, 0. Okay, so the last thing I need to tell you about is the exclusive OR and the equivalence gate. So let's look at exclusive OR. Here's A and here's B and here's C. The idea with an exclusive OR is it's either A or B, but not both. So that's where the exclusive part comes. So either A or B, that would be these two. This is neither A nor B, so that's a 0. But if you have both, that's excluded. So that's what the exclusive OR is about. Okay. What if I took the exclusive OR and inverted that? What do you think you'd get? Well, I think you could predict that pretty easily. Put these in the wrong order. Here's A, here's B, and here's the output C. All right, it's like an exclusive OR, only you invert it. So this would look like 1, 0, 0, 1. Okay, so this is called an equivalence gate because if A and B, they're the same thing. They're equal. 0 and 0, you get a 1. 1 and 1, you get a 1. If they're different, you get zeros. So this is an equivalence gate. Okay, so I think you get the basic idea of gates in less than 5 minutes. Be sure you understand this for the exam.